Hello. So good afternoon to all of you. So in last class we have seen about this boundary layer part 1. Okay. So in today class we are going to see the boundary layer part 2. Okay. So in last class what we have talked? In last class we have talked about how the boundary layer it will form. Okay, the boundary layer it will form, and we have already discussed about the viscous flow, because within this boundary layer viscous flow will exist. Outside of the boundary layer non-viscous inviscid fluid will exist. Inside this boundary layer shear stress will exist, and the flow will be irrotational flow. Okay, so today we are going to talk about the displacement thickness. Okay, today we are going to talk about displacement thickness, momentum thickness, okay, and energy thickness. So today we are going to talk about this displacement thickness that is represented by delta star. Okay, and second one is called as, that is momentum thickness, that is momentum thickness. So this is represented by theta. And last one is called as energy thickness. So this is represented by delta double star. Okay, so today we are going to see in detail about displacement thickness, and we are also going to look about the definition, what exactly it's meaning. Okay, so good afternoon to all of you. Okay, thank you. So what will happen when a flow is happening? Suppose this is my solid boundary. Okay, this is my solid boundary. So this is my free stream velocity. Free stream velocity means what? The velocity which is has not been it's contacted with the solid surface. When velocity is constant, uniform throughout the depth. Okay, still it has not been come in contact with the solid surface. So when this this is my free stream velocity. When this free stream velocity will come in contact with this solid surface, what will happen? There will be a boundary layer will be formed. What is boundary layer? The locus of the point where the velocity will be equal to 99, where the velocity will be equal to 99% of the free stream velocity. Okay, so what will happen? So due to the formation of the boundary layer, there will be reduction in flow mass rate. Okay, so what will happening? There is the mass is continuously entering into this boundary layer. From this outside of the boundary layer, the mass is continuously entering into the inside of the boundary layer. Okay, so due to this mass accumulation within this boundary layer, the boundary layer thickness is gradually increases. That's why each and every section along the length of the pipe, the boundary layer thickness is not constant. Why? Because the mass accumulation increases with increase in the length direction, with increase in length. So this is the length direction. Suppose this is my x, with an increase in x, there will be increase in mass flow rate. Okay, mass flow rate. So due to increase in mass flow rate, there is a accumulation in mass will be increases. That's why the boundary layer thickness is gradually increases with increase in x. Okay, that's why I was talking about the boundary layer thickness is a function of x. Boundary layer thickness is a function of x. Okay. So I can write down this point here as what I told. I can write it down. So what will happen? Some mass of the fluid enters into the boundary layer, in short form BL, enters into the boundary layer from outside zone of the boundary layer. Okay, I think this is clear to all of you. Now what will happen? So you see point. Okay, so due to formation of the boundary layer, what is happening? The free stream velocity is now, it is converted into a velocity gradient. So if you draw at any point, suppose this is, I'm choosing a point A. Now if at this point, what will happen? The velocity now it is reduced. Now velocity is gradually increases in perpendicular direction. It is now gradually increases in perpendicular direction. Means what? Means there will be a velocity gradient will be exist. Okay, means there is some mass. This is the mass. This is the reduction in mass. Okay, there will be some reduction in mass will occur due to the formation of the boundary layer. Okay, so I can write it down. Due to formation of the boundary layer, there will be a reduction in mass flow rate. Okay, the mass flow rate will be reduced. Okay, next point I can understand. Okay, next point is that suppose this is my solid boundary, and this is my free stream velocity. Now when it is come in contact to the solid surface, what will happen? This boundary layer is formed. Okay, this boundary layer is formed. Suppose I am choosing one section. This is section 1-1. This is section 1-1, and this one is section S. This one is section 2-2. Okay, so what will happen? Suppose this point is called as, this is called leading edge. This one is called leading edge. Suppose this is x will be equal to 0. Suppose I am choosing this section 1 at a distance from this leading edge x1. Okay, and I am choosing this section 2 at a distance from this leading edge, that is called x2. Okay, so what actually I am trying to say, the rate of mass flow in gradually decrease due to the formation of the boundary layer. That is clear. So gradually, if I move along the length of the plate, what will happen? The mass flow rate increases. Okay, the mass flow rate increases, or I can say the accumulation of the mass is increasing due to what will happen? The boundary layer thickness is here. The boundary layer thickness, see, it is gradually increases. So I can write down one point. As I move, okay, along the length of the plate or solid boundary, or I can say solid boundary. Okay, the mass flow rate increases. Okay, the mass flow rate increases, or I can say the accumulation of mass increases. Okay, so what I can say here, the rate of mass in section 2 is greater than the rate of mass in section 1. Okay, and I know this boundary layer thickness is a function of x. In last class I talked about the boundary layer thickness is a function of x. As the x will increases, the boundary layer thickness also will increases at different section. So I can say, as here x2 is greater than x1, so I can, this is delta 2 and this is my delta 1. So I can conclude that the boundary layer thickness at section 2 is greater than the boundary layer thickness at section 1. Okay, the boundary layer thickness means what? The boundary layer thickness is only due to the mass accumulation. Okay, the mass accumulation, remember this one. So I can say one point is that the formation of boundary layer, is due to the accumulation of mass. So let me accumulation of mass. Okay, fine. Now what will happen? So as the mass rate is entering into the boundary layer from outside, what will happen? So I already told you there will be some reduction in mass. Okay, there will be some reduction in mass will have there. So this is my solid boundary, or this is my plate, solid plate. This is my free stream velocity. Okay, this is my free stream velocity. Okay, this is u infinity. Okay, this is my free stream velocity u infinity. And when it is contact to the solid surface, the boundary layer will form. Okay, the boundary layer will form, and what will happen? There will be some reduction in mass. There will be. So this is my reduction. This shaded area. This is my reduction in mass. Okay, this is called reduction in mass. Okay, so what is saying? So mass has been reduced. The mass has been reduced due to the formation of the boundary layer. Okay, so this displacement thickness, that is, if you understand the displacement thickness, that is a mathematical value, or that one is a assumed value. We cannot do physical observation of that one. Okay, the displacement thickness, momentum thickness, energy thickness, we cannot visualize in naked eye. Okay, that is a mathematical value or assumed value. We can only assume that one. Okay, so so that is actually, I'm going to say displacement thickness. What is exactly saying? The rate of mass which has been reduced, due to the formation of the boundary layer. Okay, due to the formation of the boundary layer, what is happening? There is a reduce in mass flow rate. Okay, so in order to compensate the reduction in mass, the amount of distance displaced by the plate in perpendicular direction, that is known as displacement thickness. First of all, understand that one, then I will go to the proper definition. Okay, what exactly I am saying? Due to formation of the boundary layer, there will be reduction in mass flow rate. Okay, there will be reduction in mass flow rate. Okay, fine. Now in order to compensate this reduction, the reduction in mass flow rate, the plate to be displaced certain distance in perpendicular direction. What exactly I am trying to say? Suppose this is my solid boundary. Okay, this one is solid boundary. Okay, so what is happening? This is my velocity distribution, and this one is my reduction in mass. This one is my reduction in mass flow rate. So in order to compensate this reduction in mass flow rate, we have to shift, or we have to displace this solid boundary in this perpendicular direction, and the distance by which it has been displaced, that distance is called as displacement thickness. I think you clear about this one. Okay, again I am repeating. So in order to compensate the reduction in mass flow rate, the distance displaced by the solid boundary, in perpendicular direction, the distance is called as displacement thickness. Okay, so if you want to write down, just for the sake of understanding, we can write down. So amount of distance, okay, the amount of distance displaced by the plate, in order to compensate the reduction in mass flow rate, Okay, that is called as, that distance is called as, that distance is called as displacement thickness. The distance is called as displacement thickness. Okay, so this distance is called as displacement thickness. So as there is a reduction in mass due to the formation of the boundary layer, so definitely there will be reduction in momentum also, because momentum will be equal to mass into velocity. If there is a reduction in mass flow rate, definitely there will be reduction in momentum. And if there is a reduction in mass flow rate, definitely there will be reduction in kinetic energy of the fluid, because kinetic energy is half mv square. That is nothing but is called as energy thickness. That is called energy. Okay, so I can say H there will be a reduction. There will be reduction in mass flow rate. Mass flow rate. Okay, due to the formation of, why there is reduction? Due to the formation of boundary layer. Due to the formation of boundary layer. Okay, due to the formation of the boundary layer. So definitely there will be a reduction in momentum. There will be reduction in momentum, and also there will be reduction in energy also. Okay, energy, that is called kinetic energy. Okay, so if you define this momentum thickness, if you defined, how can you define? So momentum thickness is like that: the amount of distance displaced by this plate in order to compensate the reduction in momentum, that is called as momentum thickness. Similarly, if you define the amount of distance displaced by this solid boundary in order to compensate the reduction in energy, that is called as energy thickness. So if you understand the proper definition, it is asked in your exam. So what is the proper definition of the, Okay, what is the proper definition? The proper definition of first one is what? That is called displacement thickness. It is called displacement thickness. That is represented by del star. Okay, so the proper definition: the distance measured perpendicular to solid boundary, by which the solid boundary must be displaced to compensate reduction in mass flow rate. That is called as displacement. What is displacement thickness? The distance measured perpendicularly to the solid boundary. If you understand in figure, so this is my solid boundary. Okay, this is my solid boundary. Okay, so the distance measured perpendicularly to the solid boundary, okay, by which this solid boundary must be displaced. Suppose it is displaced to this distance. Okay, this is the distance displaced by this solid boundary. So this distance displaced, why displaced? In order to compensate the reduction in mass flow rate. This distance is called as displacement thickness. Okay, that is called as displacement thickness. Okay, so now if you write down the definition of the momentum thickness, how if you write down? So if you write down the definition of momentum thickness, this is called momentum thickness. Momentum thickness represented by this one is theta. Same definition, the distance so the distance measured perpendicular to the solid boundary, perpendicular to solid boundary, by which the solid boundary must be displaced in order to compensate the reduction in momentum. That one is called as momentum thickness. Means what? If there will be reduction in mass, definitely there will be reduction in momentum, because momentum will be equal to mass into velocity. So in order to compensate that reduction in momentum, the amount of distance displaced by the solid boundary in this perpendicular direction, that distance is called as momentum thickness. Okay, that distance is called as momentum thickness. Similarly, if you write down the definition of the energy thickness, how can define? That is called energy thickness. Okay, energy thickness, that is represented by delta double star. Okay, so same you write it similarly, the distance measured perpendicularly to the solid boundary by which the solid boundary okay, that is must be displaced okay, in order to compensate the reduction in energy, that is kinetic energy, or we can say change in energy. Okay, change in energy, that is called as displacement thickness. Okay, displacement thickness. So today we are going to derive the derivation of the displacement thickness. First of all, today we are going to do today in lecture we are going to do derivation of displacement thickness. That is represented by what? That is represented by delta star. Okay, that is represented by delta star. So this, understand it very carefully. Suppose this is my solid boundary. Okay, this is my solid boundary. Okay, this is my solid boundary, and this is my free stream velocity. This is my free stream velocity, means the velocity is uniform. The velocity is uniform throughout. Okay, and the velocity will be u infinite. Okay, So when it is come in contact with the solid surface, this one is called solid boundary. Okay, when it has come contact with the solid boundary, what will happen? The boundary layer will be formed. Okay, there will boundary layer will be formed. Okay, so suppose I am choosing a particular point. Suppose I am choosing this point as a. Okay, so at this point, let me draw the velocity gradient. The velocity gradient will be like this. The velocity gradient will be like this. Is my velocity gradient. Okay, and this is my y direction. This is my y. So suppose I am choosing a small strip at a particular perpendicular distance y from the solid boundary. I am choosing a very small strip. This is my small strip of thickness is, that is dy. Of thickness will be dy. Okay, and suppose the width of the solid boundary will be, this is my width of the solid boundary. This is my width of the solid boundary, and that is represented by b. Okay, and this length of the length of the solid boundary will be, this is my length of the solid boundary. Suppose this is my L. Okay, this is my L. Okay, this is my L. And this point is called as, leading edge. Okay, or where x will be equal to 0, and this point is called as trailing edge. Okay, this is x will be equal to here L. Okay, so now if you see the side view, of the strip, if you look from this side, if you draw the strip, how it look like? It look like, if you draw the side view of this strip, how it will look like? If you look from this side, this will be your width. Imagine this one, this will be your width, and the thickness will be what? This one will be your dy. What is the area of this element? Okay, what is the area of this element? So this dA will be what? This is b into, this is dy. Okay, this is b into dy. So this dA is what? This dA is called as, this is the area of the flow element. So this is area of flow in element. This is elemental area. Okay, now if you consider at the distance of y, at this layer the velocity will be, this is small u. Okay, at this layer the velocity will be small u. What is this small u? Small u is called as velocity of fluid. This is called velocity of fluid. Velocity of fluid flowing through element. That is flowing through element. Okay, suppose u is the velocity which is flowing, and u is definitely less than infinite. So u is less than the velocity, free stream velocity, it is for sure. Okay, so u is less than the free stream velocity. Okay, so suppose I am taking case 1. Suppose case 1, when there is boundary layer is not present. Okay, first case, when there will be no boundary layer. There will be no boundary layer, means there will be no formation of the boundary layer. What is the case when there will be no formation of the boundary layer? Means the rate of mass which is in flow. Suppose there will be no formation of the boundary layer, the free stream velocity will be what? This is my free stream velocity. Okay, this is my free stream velocity. Okay, and this is my solid plate. This is my solid plate. Okay, when there is no formation of the boundary layer, the rate of mass flow through the element. That element you have chosen, na? So this is the, suppose this point A. What will happen when there is boundary layer will not be formed? There will be no reduction in mass. Okay, there will be not reduction in mass, and there will be no velocity gradient will be formed. So whatever the mass will be formed, whatever the mass will be in flow in this elemental area, whatever the mass will be in flow into this elemental area, that is dy thickness. Okay, and this is my plate thickness, is this one is my b. Okay, so through this one the velocity will be remain constant because there is boundary layer is not formed, so there will be no reduction in mass flow rate. So if you write down the mass flow rate, to write down the flow rate mass flow rate through this element, through the element dA, area of dA. What is the mass flow rate? Okay, suppose I am writing this one as dm1. Okay, that is what, this is rho into this area into this free stream velocity. Velocity is not, has been not reduced, the velocity will be remain constant as there is no formation of the boundary layer. So this is rho into this is u infinity. What is this a? A is what? A is, if you see the side view, if you look from this one, the side will be this is my b. Okay, this is my b and this one is my dy. Okay, what is the elemental area of this one? This is b into dy. So I can write down here, this is b into this is dy into this is u infinity. So this is equation 1. So this equation will be, the rate of mass will be when there is no formation of the boundary layer. Now second case, if there is a formation of the boundary layer. Okay, now in second case, if there will be formation of the boundary layer, what will happen? Definitely there will be reduction in mass flow. Okay, due to the formation of the boundary layer, the mass, there will be reduction in mass flow rate due to reduction in velocity gradient. Okay, now case 2. Okay, when the boundary layer, okay, when boundary layer is present, when the boundary layer is present, so what will happen? This is my free stream velocity and this is my free stream velocity. Okay, this is my free stream velocity. Okay, understand this very carefully, very important thing. If you can understand this derivation, you can solve any problem in your exam. So now the boundary layer will be formed. Suppose this point I have chosen this point as A. Okay, now there will be a velocity gradient will be exist. Now the free stream will is converted into a velocity gradient. Okay, now I have chosen a point at a distance of y, and suppose this thickness I have chosen, this elemental thickness will be, this one will be a dy. Okay, and here is the velocity of this elemental, the velocity of the fluid which flow inside this element, that is u. Okay, now if you, this is my width of the plate, this one is my width of the plate, and this is length. So if you see the side view, from here, how it will look like this element? If you look like from the side view, this one is my b and this is my dy. What is the area of this element? The dA will be equal to, this is b into dy. Now if you write, what is the mass flow rate? If you write the mass flow rate, when there is a formation of the boundary layer, suppose I am writing this one as dm2. Okay, that will be equal to rho into this is a. Now there is no free stream velocity. Now the velocity has been reduced. Which is less than the free stream velocity. So I can write down this is u. Okay, so what is this a? That is called b into this is dy into u. This is equation 2. Okay, so now as this u is less than u infinity, you can observe one point, that this mass flow rate, the mass flow rate will be less than the mass flow rate 1. Why there is a reduction? Because the formation of the boundary layer. So the mass flow rate in second case will be less than the mass flow rate in first one due to the formation of the boundary layer. If you subtract this equation 1 and equation 2, what we get? That is the reduction in mass flow rate. We have to find out the reduction in mass flow rate. Now if you to find out, so due to the formation of the boundary layer, there will be reduction of the mass flow rate. Now what is the reduction? Now you can find out the reduction in mass flow rate. The reduction in mass flow rate, that is represented by del m. Okay, so this del m I can write it down, that will be equal to, this is dm1 minus this is dm2. dm1 is what? Delta. This dm1 is called the mass flow rate when there is no formation of the boundary layer, and dm2 is called the mass flow rate when there will be formation of the boundary layer. If you subtract it one, what will you get? The reduction in the mass flow rate. Okay, so if you put this one, that is coming out to be rho into this is b into dy into this is u infinite minus this is e. So this is the reduction in mass flow rate. Okay, this is the reduction in mass flow rate at what distance? At y distance from the solid boundary. Okay, at y distance from the solid boundary. Now we have to find out the entire mass reduction in mass flow rate throughout this boundary layer thickness. Okay, you have to find out what is the reduction in mass flow rate entire about this boundary layer thickness. So what you have to do? You have to do the integration. Okay, we have to do the integration. Okay, so we can write down this del m is the mass flow rate. Del m is the mass flow rate. Del m is the reduction in mass flow rate. Okay, that is better. Del m is the reduction in mass flow rate. Okay, for a distance y from the solid boundary. So in order to find out the total reduction in mass flow rate. Okay, mass flow rate. So what you have to do? We have to do the integration. Okay, so now if you write down, so if you understand this thing, so this is my solid boundary, okay, and this is my velocity at this point A. The velocity gradient will be this one. Okay, this is my velocity gradient. Okay, and I have chosen at a distance y a small elemental strip having a thickness of dy. Now I found out what is the reduction in mass rate about this elemental strip. Okay, now what I have to do? I have to find out the mass flow rate about this entire boundary layer thickness. Okay, about this entire boundary layer thickness, and this mass flow rate will keep on changing as the boundary layer thickness is keep on changing with respect to the length direction. If you move along the length direction, in this direction, the boundary layer thickness is keep on changing, so the mass flow rate also keep on changing. Okay, so I am finding out this mass flow rate at this point number A. Okay, so if you find out the total reduction in mass flow rate, what is the total reduction in the mass flow rate? That is nothing but integration of this b into this dy into this u infinity minus u. What is the limit? 0 to this is delta. This is equation number 1. Okay, now if you go to the definition of this displacement thickness, what I told the definition of the displacement thickness, if you go to the definition of the displacement thickness, what I written? A distance measured perpendicular to the solid boundary by which the solid boundary must be displaced in order to compensate the reduction in mass flow rate. Okay, suppose for example suppose this is my solid boundary. So if you understand the definition, from the definition I am taking the help. So suppose this is my solid boundary. Okay, so what is the definition is saying? So the amount of distance displaced perpendicularly from the solid boundary, okay, in order to compensate the reduction in mass flow rate, that distance is called as this displacement thickness. Suppose the boundary has been displaced to this one, so this is the distance which is displaced by this boundary to this one, so this distance is called as displacement thickness. Okay, so in order to compensate the reduction in mass flow rate, the solid boundary has to be displaced to a distance of this delta star. Okay, and the velocity of flow Now it has been reduced. The mass flow reduction in mass flow is compensated. So what is the velocity in this zone? The velocity in this zone will be equal to free stream velocity, because the distance already it has been shifted in order to compensate in the reduction in mass flow rate. So now the free stream velocity will come. Okay, now you will not come, the free stream velocity will come. Now suppose this is now my width of the plate. This is now my width of the plate. Now what will happen? There will be free stream velocity will exist. So now this is my free stream velocity. Okay, similarly same, if you choose a distance y, if you choose a small strip of thickness dy, what is the mass flow rate here? Okay, what is the mass flow rate here? So if you see from side view, this side view, this is my side. Okay, and this will be my b, and this is my dy. This is my dy. Okay, so what is this dA? This dA will be equal to, this is b into this dy. Okay, this dA will be b into this dy. Now I can say, for what is the mass flow rate now here? Okay, we write down what is the mass flow rate. What is the mass flow rate here? This is rho into area is what? This dy is now, this is delta star. So this dy is now, this is called delta star thickness. Okay, so I can write down this thickness will be delta star into this one is how much? B into this u infinite. This is equation 2. Okay, this is the compensation in mass flow rate. I can write down this one is compensation in mass flow rate. So this equation 1 means total reduction in mass flow rate must be equal to the compensation in mass flow rate. Okay, the definition is saying the displacement thickness. So now if you equate this equation 1 and 2, so what is saying? the compensation in mass flow rate, the compensation mass flow rate must be equal to the total reduction in mass flow rate. Okay, so what is the compensation? The compensation will be equal to rho into this is delta star into this is b into this is u infinite, must be equal to the integration of 0 to delta, that is rho into b into this is dy into this u infinite minus this is u. Now b density, b in gone, the density and b will be gone. Now if you find out from this one what is the displacement thickness, displacement thickness will be equal to 1 by u infinite into this is 0 to delta. Okay, and this is u infinite minus u into this is dy. Now again if you rewrite this equation, delta star will be equal to this is 0 to delta, okay, into 1 minus this is u by this is u infinity into this is dy. This is called as my displacement thickness. This one is called as displacement thickness. Okay, this one is called my displacement thickness. So displacement thickness you can get the numerical in your exam. So displacement thickness, again you write the formula will be the 0 to delta into this is 1 minus u by this will be u infinity into this is dy. Okay, so here the velocity at a particular distance y, the velocity at a particular distance y, it will given in the form of u infinite. Okay, it will give here like this u will be equal to 1 minus y by delta into this y infinity. It will give here by this equation. So now you have to find out, it will be asked to you have to find out this displacement thickness. Okay, so that is the thing it will come. So in next class I am going to derive the formula for the momentum thickness, okay, and that is energy thickness. Okay, momentum thickness and energy thickness. So Ashish Acharya is asking, please again say the compensation mass flow rate. Okay, see, the actual meaning is, see, when there is a formation of the boundary layer, when there is that the boundary layer, when it will form, what will happen? The mass flow rate, whatever the mass flow is entering into this boundary layer, there will be reduction in mass flow rate. Okay, so in order to compensate the reduction in mass flow rate, or in order to keep the free stream velocity as it is, okay, so the plate is to be displaced, the perpendicular solid boundary is to be displaced certain distance from the reference one, from its original one in perpendicular direction. So how much distance it has been displaced, okay, how much distance it has been displaced in order to compensate the reduction in mass flow rate, that distance is called as displacement thickness. That distance is called as displacement thickness. Okay, so now we are going to solve the assignment question which I given in yesterday class. Okay, so the first question, you see, the first question, the first question it is saying, so this is the first assignment question. So the venturimeter is there, this is my venturimeter, okay, and it has been connected like this, and this is my throat, okay, and this is my like this, and this is my venturimeter. Okay, now this is center line of the venturimeter, this is my center line of the venturimeter. Suppose this is my inlet of the pipe, this point is called as inlet of the pipe, and this point is called as throat of the pipe. Now if you connect one manometer, U2 manometer through this one, so now I have connected one U2 manometer to this both point. Okay, this is I'm connected one U2 manometer to this both point. Okay, so what will happen? Velocity is reduced, so pressure will here will increase, the velocity will increase at this point number 2. So this is point number 2 and this is point number 1. So velocity increases, pressure will be reduced, so the deflection will be like this, the manometric fluid will be displaced like this. Okay, so what are the given data are there? So the given data are, the dia of the pipe. So dia of the pipe, I'm writing this is capital D, that is given you, this is 200 mm. Okay, and the discharge in this pipe, the discharge is given to us as, this is 62.8 liter per second. Okay, and pressure at this point number 1, pressure in the pipe, it is given you 100 kilopascal, that is gauge value it is given to us, that is gauge value. Okay, and the atmospheric pressure is given to us, this is 101.3 kilopascal. Okay, and the vapor pressure, it is actually the vapor pressure will be, it is has been asked told in the problem, the vapor pressure will be exist at the throat portion, means at this point number 2. What is the vapor pressure? That is 2.39 kilopascal, that is 2.39 kilopascal. So it is asking to find out what is the throat diameter. Okay, so now I am applying the Bernoulli equation in between the point 1 and point 2. Okay, so now I am applying, here I am choosing, actually as it told, this point number 2 is at a distance higher, 2 meter higher than this inlet point. Okay, so this is the point, this is the point reference, this is one, so this one is at a distance of, this one is 2 meter. Okay, so this one is a distance of 2 meter. Suppose I am assuming this one as my datum line, so I am assuming this one as my datum line. Okay, datum line means what? Z1 will be equal to 0. Now I am writing down this Bernoulli equation in between point number 1 and point number 2. So what is this? P1 by rho g plus this is Z1 plus this is B1 square by 2g will be equal to, this is P2 by rho g plus this one is Z2 plus this is B2 square by 2g. Okay, now if you take this one P1 by rho g plus this Z1, okay, this one minus this is P2 by rho g plus this one is Z2 will be equal to what? This is B2 square minus b1 square by this one will be equal to 2g. This is I am taking to equation 1. So if in equation 1 you can able to find out the piezometric head difference, okay, this is the piezometric head difference, then we can find out, there is no problem. Okay, so we have to find out this one. So this is p1 by rho g plus this one is z1 minus this is p2 by rho g plus this one will be z2. What is the p1 by rho g? So p1 is given how much? 100 kilopascal, that is given in gauge value, but pressure at this throat point, it is given vapor, that is vapor pressure, which is given in absolute. Okay, so pressure at point 1 must be written in the form of gauge value, a absolute value. Okay, so this will be equal to 100 plus the atmosphere pressure, which is 101 point, this is 3 kilopascal. So this is pascal, kilo, in order to convert into pascal, in 10 to the 3, divided by this one is density of water, this is 1000 kg per meter cube, into this is 9.81, plus z1 will be 0. Okay, so this is my piezometric head at this point number 1, minus the p2 by rho g. P2 is how much? This is 2.39 into this is 10 to the power 3, divided by this is 1000 into this is 9.81, plus z2 will be how much? This is 2 meter. Okay, now if you solve this is coming out to be 20.51 minus this is 2.243, so this is coming out to be 18.27 meter. Okay, now we got this value. Okay, now we got this value. Now we can use this discharge formula directly, we can use. So this q will be what? Q will be equal to a1 into a2, this is root over of this is a1 square minus this a2 square. Okay, a2 square into this is root over of 2g into this delta h. Okay, this is delta h. So you can use this formula, but here is we can find out this b2 square minus b1 square by 2g will be this one. Okay, this will be this one. So directly we can use this delta h will be equal to, the delta h will be nothing but this is del p by rho g only. Okay, this is del p by rho g. Okay, we found out this del p, we already found out. Now I can put the discharge will be equal to, so this is pi by 4 d1 square into capital D, or let me write this is d2 square divided by this one will be d1 to the power 4 minus d2 to the power 4 into this is 2g into this is del p by rho g. Okay, so now this q is given to us. What is the value of the q is given to us? This q is given to us, this is 62.8 into this is 10 to the minus 3. Okay, so now this is pi by 4 into d1 is diameter of the pipe, this is 200 millimeter, this is 0.2 meter square, into we have to find out this throat diameter, into the divided by this will be equal to 0.2 to the power 4 minus this is will be this d to the power 4 into this is 2 into this 9.81 into this one is 18.27. Okay, so now if you solve this equation, you will get the diameter is coming out to be 0.064 meter, or this is coming out to be 64.80 millimeter. This is my answer. This is the answer for this question. CD is not given means you have to take CD as 1. Coefficient of discharge is not mentioned means the coefficient of discharge you have to take in 1. If it is mentioned, then you have to take, otherwise you have to take it is a 1 value. Okay, so now we will go to the next question. So the next question is saying, so a pipe is there now it has been expanded. So now it has been expanded to certain diameter. This is my pipe. Okay, this is the length direction of the center line of this pipeline. Okay, suppose this is point number 1 and this is point number 2. Okay, and the flow is occurring in this direction, this is Q. Okay, and see the point number 1 is at a distance of how much? The point number 1 at a distance of this distance is how much given? This is given you as 6 meter. This is given as 6 meter. Okay, and diameter of this one, diameter at this one, it is given 20 centimeter, and this diameter at this point number 2, it is given you as 40 centimeter, and pressure at this point 1, it is given you as 120 kilopascal, and pressure at this point number 2, it is given you as 80 kilopascal, and the discharge through this pipe, it is given you as 200 liter per second, and it is asking the head loss. Okay, it is not asking the head loss due to sudden expansion. It is asking head loss mean there will be head loss sudden expansion plus the head loss will be due to friction also will be there. It is asking total head loss of the pipe. Okay, now we apply the Bernoulli equation in between point number 1 and point number 2. So applying Bernoulli equation in between point number 1 and point number 2. Okay, so that is P1 by rho g plus this is Z1 plus this one is V1 square by 2g will be equal to this is P2 by rho g plus this is Z2 plus this is will be P2 square by 2g. Okay, plus this is head loss. We have to find out this plus this head loss. So now I am choosing this one as my datum line. So now I am choosing this one as my datum line. Okay, datum line means what? Z1 will be equal to 0, and at this Z2 will be equal to how much? 6 meter. Okay, so now if you put this value, so what is this P1 P1 by rho g? How much this is? I am taking P1 by rho g plus this is Z1. Okay, and P1 by rho g into this Z1. If you directly put no problem. So let me this is P1 by Z, this is plus B1 square by 2g minus this is B2 square by this one with 2g. Okay, minus this is P2 by rho g plus this one will be Z2 will be equal to head loss. Okay, now I have to find out B1 and B2 first of all. So continuity equation, if you use the continuity equation, so B1 will be what? This is Q by A1, and B2 is how much? This is Q by this is A2. Okay, so this B1 will be equal to Q is given how much? It is 200 liter per second is given. So this is 200 into 10 to the power 3 minus 3 meter cube per second. In the area will be this pi by 4 into this is 0.2 square. Then B2 will be equal to how much? This is 200 into 10 to the minus 3 meter cube per second. This is pi by 4 into this is 0.40 square. Now if you see, B1 is coming out to be 6.37 meter per second, and this B2 is coming out to be 1.59 meter per second. Okay, meter per second. Now you put this value and find out the head loss, total head loss. So this is P1 by rho g, how much? This P1 by rho g will be 120 into 10 to the 3 Pascal divided by rho g. Water is flowing, so density of the water is 1000. This is 9.81 plus Z1 is 0. Okay, this is 0 minus, okay, minus if you see this is minus this is P2 by rho g. P2 is how much? 80 into 10 to the power 3 Pascal divided by this 1000 into this is 9.81 plus Z2 is how much? This is 6 meter. This is 6 meter. Okay, and next what is saying? Plus B1 square minus B2 square by 2g. So this is plus B1 square is how much? 6.37 square minus B2 square is 1.59 square divided by this is 2 into 9.81. That is will be equal to total head loss. Okay, so now if you find out the head loss, total head loss, that is coming out to be 0.016 meter. This is my answer. 0.016 meter. Okay, So now actually the assignment you submit, I will create a Google Classroom. Okay, I will create a Google Classroom, and you circulate that code with along with all the students, so that you can join in that classroom automatically, and you upload the assignment there. And I will put a link also for your class test. This for your class test, I will upload a link in that Google Classroom, so that you will get that link and click that link and appear for the online test. There will be online test will be there. I will let you know when the test I will conduct. When the test I will conduct, I will intimate you. I will actually inform you. So thank you all. Okay, thank you for today. Thank you all for watching my video, for watching this video. Okay, and please, if you like my video, please like button, you please hit this like button. This is free of cost. Okay, and please share, this is also free, and subscribe for more update. Okay, so these three things you do. And the password for today attendance will be the password for today attendance will be, that is 1308. 1308. This is valid for 10 minutes today. This is valid for 10 minutes. Now the time will be 5.02. This is PM. Okay, so exactly it will finish by 5.15 PM. It will be invalid that time. So thank you all. Thank you so much. Thank you. So enjoy it at your home, study, and thank you all.